Hello students, welcome to Sourav's classes. We are discussing about the aromatic heterocyclic compounds, and here we are today we will discuss some about some aromatic heterocyclic compounds. In our previous video, we have discussed about furan and thiophene, which are the aromatic heterocyclic compound. Furan contains oxygen as a heteroatom and thiophene contains sulfur as the heteroatom. Now today we are now considering this pyrrole first. This is the 5-membered ring with heteroatom nitrogen. This pyrrole is mainly formed by when furan is treated with ammonia and water when passed over heated alumina. The mixture of ammonia, water and furan, when passed over heated alumina, furan is produced. The reaction is like, pyrrole is produced. This is furan plus NH3, hot Al2O3 and water, moisture, and this gives us pyrrole. So this pyrrole is formed by reaction of this. This is your furan with ammonia and moisture over hot alumina. Again, it is also prepared by heating ammonium mucate. This is the number 1, ammonium mucate, heating ammonium mucate and the reaction is like this: H4N OO CHO CHOH whole 4 COONH4. This compound, this is ammonium mucate. This when reacts with when it is heated with glycerol, we get this pyrrole compound. We get the pyrrole plus 2CO2 plus NH3 plus H2. So these are the reaction. When this ammonium mucate is heated with glycerol, this pyrrole is produced. This is NH. Along with carbon dioxide, ammonia and water. Another method of preparation of pyrrole derivative is reaction of 1,4-diketone with ammonia, and this ammonia reacts with attacks here first in this any one of these carbonyl group, and this first of all let us consider this, it is attacking here, and this bond is open, and this OH one this NH3 when attacked here, this NH3 when react here, it is producing NH3 plus, and the one hydrogen is removed from NH3 to OH. So we are getting here NH2 and OH. If we want to write this previous step, actually this happens like this way. O minus NH3 plus, and here we have one CH3, and here we have C double bond O, and this is CH3. Now after the attack, and one hydrogen is removed from CH2, suppose H, and you can write the positive charge in the here. So this hydrogen is removed and it is shifted from here to here. That's why we are getting this product. And now this lone pair of nitrogen, now it is attacking here, and this bond is opening. So this we get this compound, and again here from here one hydrogen is removed and it is attached here. Now we are getting this compound, and on heating this compound, 2 molecules of water is eliminated. 2 molecules of water is eliminated, and we are getting this 2,5. If we, this number 1 carbon, 2,5-dimethyl pyrrole. So this is one of the important synthesis of pyrrole derivative. If we use this amine derivative instead of ammonia, then we will also get the substituted pyrrole here. So that means N substituted N-alkyl pyrrole, and that is why this reaction is very much important for production of substituted pyrrole or pyrrole derivatives. This pyrrole exists as a resonating hybrid of the following structure. In the structure of pyrrole, we can say it exists as resonating structure, as a hybrid. It exists as a hybrid of the resonating structure of following. It shows that now this lone pair over this nitrogen atom, it gets conjugated with the pi electron in the ring. So we are getting this one. Now this nitrogen is now positive, and this one is negative. Now this can there is one double bond here. Now this can resonate here, move here, and this pi bond can resonate here. So we are getting this product. This one, it is negative here, and N, H, this is positive here. So this is another azerotic form, and again if this nitrogen moves, this lone pair moves in this direction, So we will get this product also. You can write it here also like this. If it moves in this direction, that is, if this lone pair is moving in this direction, then we get here one double bond, and this bond is remain intact, and we have so this bond, if it is moving in this direction, this lone pair is moving in this direction, then this bond will move in this direction, so we will get negative sign here. Similarly, if this lone pair moves in this direction and this pi bond moves in this direction, we will get another resonating structure. So this is the third, this is another resonating structure. So this pyrrole molecule actually is a hybrid or by hybrid of this all five resonating structure. So this and this pi electron and this lone pair over the nitrogen atom is remain delocalized with the ring. So this is the actual form of the pyrrole. Regarding the reactivity of pyrrole, we see that in case of pyrrole, this lone pair over nitrogen atom, it is involved with the aromatic, involved in maintaining the aromaticity of the ring. So to maintain the 4n plus 2 pi electron, it is 4n plus 2 pi electron, these two electrons, these two pi electron, these two pi electron, and these two electrons of the nitrogen are involved in aromaticity. So it is so the its availability over the nitrogen atom is less. That is why we have shown in the resonating structure that this lone pair can be resonated with this pi electron. So its availability over the nitrogen atom is minimum. That's why its basicity is low compared to pyridine. Pyridine, in case of pyridine, you will find that here this nitrogen is this lone pair of nitrogen is not involved in the aromatic ring. That is why it is that is why this is more available for donation to proton. So in general, the basicity of pyridine is greater than pyrrole. Now here basicity is considered in terms of considered in terms of Lewis basicity. That is, here both nitrogen, lone pair of nitrogen can be donated to a electron deficient species. Like you can consider it like proton, H plus ion. So in case of donation of electron to proton, here feasibility of pyridine is greater than that of pyrrole, because this lone pair is less available compared to this one. Moreover, in acid medium, this pyrrole undergo some polymerization reaction, like here we are using dilute acid, and we are getting this compound. joined here. And there is another molecule. It is joined here. So this molecule, this pyrrole molecule is this is a polymeric structure. Polymeric structure. Such structure is obtained, such compound is obtained when pyrrole is treated with dilute sulfuric acid. For this is stable for this structure is stable for half an hour. Now, in other reactions, we are coming with the other reactions where this imino group is imino hydrogen is replaced. Replacement, next part is the replacement of imino hydrogen. Now this is another type of property, another type of reaction that pyrrole undergo, that we are coming now about discussion. The imino group present in a pyrrole that can be replaced, that this group, this hydrogen can be replaced by methyl group or acyl group, and this is one of the important reaction for pyrrole. And if it is treated with this, pyrrole is treated with when it is treated with KOH, we are getting this type of compound, N minus and K plus. Then the potassium salt is formed and plus water. Similarly, when it is treated with methyl iodide, CH3I, we are getting this product, CH3 plus this reaction taking place at 60 degrees centigrade, and if it is treated with this is substitution of methyl group, substitution of this hydrogen group by methyl group, and it can also be done with CH3 COCl at 80 degrees centigrade. Here this hydrogen is substituted by acyl group, that is the product is nitrogen OCO CH3. So this is the product. So here we can convert all this imino hydrogen that is here by methyl group or by acyl group or simply by potassium, making a potassium salt. Now next reaction is reduction. if we take reduction of pyrrole, the reduction takes place for pyrrole if we take this is our pyrrole. When it is reduced to zinc and acetic acid CH3COOH, we are getting the compound like this one. One double bond has already been reduced, and here we are finding 2 hydrogen atoms here. This carbon is getting saturated. It was previously unsaturated, now it is getting saturated. And after that, for prolonged reduction in hydrogen in presence of nickel catalyst, we found this type of product. That is the entire saturated product. So these 2 type of products are obtained. This is called the pyrroline, and this is pyrrolidine. So reduction follows first saturation of 1 double bond and followed by saturation of 2 double bond, and so all these carbon get saturated during reduction. Further, pyrrole is reduced to pyrrolidine when treated with hydrogen at 200 degrees centigrade in presence of nickel catalyst. When this pyrrole is treated with hydrogen, 3H2 plus 3H2. This is nickel catalyst at 200 degrees centigrade. We found the product is pyrrolidine. All these unsaturated bond are get saturated. This is the pyrrolidine. And this is your our pyrrole. Now, if we take next is our oxidation of pyrrole. Next comes oxidation of pyrrole. This oxidation of pyrrole takes place. We oxidize this pyrrole with chromic oxide and in presence of sulfuric acid. We found that it is oxidized in presence of CrO3 plus H2SO4, and we are getting the compound of This is succinamide. Succinamide. Succinamide is formed when this pyrrole is oxidized in presence of chromic oxide, CrO3 and sulfuric acid. Next is our electrophilic substitution. Electrophilic substitution. Now this electrophilic, now here since pyrrole is a aromatic compound, and we know that aromatic compounds are more susceptible to electrophilic substitution than nucleophilic substitution, because the ring is highly electronically charged. So nucleophile or any negatively charged species come in contact with or come in closer with this ring, aromatic ring, it is repelled, while the electropositive species can attack at this highly electronically rich or high electron density, a ring of high electron density, which can be replaced, which can be the hydrogen of this ring can be replaced by electrophile. So this type of pyrrole can be substituted by electrophilic substitution, as we find in case of benzene or naphthalene or pyridine, etc. Now, when pyrrole is treated with acetyl nitrate at -10 degree centigrade in presence of acetic anhydride and dinitrogen pentoxide, we found 2-nitropyrrole. This is a substitution reaction. Here, this second hydrogen in second position, it is being substituted by the nitro group. Other substitution reactions are as follows. Suppose if we have pyrrole and it is treated with, suppose it is treated with bromine in presence of acetic acid. Now pyrrole is treated with bromine in presence of acetic acid. We are getting this compound NH. This is Br, and this is 2-bromo pyrrole. 2-bromo pyrrole, and when it is treated with iodine, I2 molecule is required. When it is treated with iodine, we are getting this tetraiodo product. Here all the 4 hydrogen is replaced by iodine. Here all the 4 hydrogen is replaced by iodine, and here the compound is named as idol. compound is named as iodole, iodole. Compound is known as iodole. So here we found that when we react with iodine, all the four hydrogen of pyrrole is replaced by iodine. So these are the all electrophilic substitution reaction that takes place in pyrrole. There are some other important reactions of pyrrole, one of which is Wilsmeyer-Hack reaction. In this reaction, this pyrrole is treated with dimethyl formamide. Pyrrole is treated with dimethyl formamide, HCONCH3CH3. This compound is known as dimethyl formamide. Dimethyl formamide. And this, when treated with phosphorus oxychloride, this gives us the aldehyde derivative of pyrrole. This one, the aldehyde derivative of pyrrole. So this is one reaction, important reaction for preparation of carbonyl compound derivative of pyrrole. This is number one. Another reaction is this is Hauben HOS Hauben-Heuss reaction. In this reaction, this pyrrole is treated with methyl cyanide. Pyrrole is treated with methyl cyanide in presence of zinc chloride and HCl. When an intermediate product is formed, this type of product is formed, which on further hydrolysis, which on further acidification gives us a compound like COCH3. This is the acetyl derivative. Of pyrrole, which is formed by Hauben-Heuss reaction. Again, when pyrrole is treated with hydroxylamine, it produces succinic acid dioxide type of compound. Then that reaction is given as this is when treated with hydroxylamine NH2OH, 2NH2OH. This gives us CH2, CH, double bond N OH, double bond N OH. This is the dioxane derivative of succinic acid. Dioxane derivative of succinic acid plus ammonia. This pyrrole also reacts with Grignard reagent. Pyrrole reacts with Grignard reagent. Like plus magnesium CH3 MgI, methyl magnesium iodide. Then it produces MgI plus methane. Methane is produced here, and then this MgI, when treated with carbon dioxide, when this compound is treated with carbon dioxide, corresponding acid is produced. So this when it is treated with methyl magnesium iodide, this is Grignard reagent. This produces this magnesium complex, and this compound, when treated with carbon dioxide, it produces the corresponding acid derivative of pyrrole. Again, when it is this methyl derivative when this is reacted with these two molecules, when reacted, I'm sorry, extremely sorry. See, this methyl magnesium derivative, that is the Grignard derivative, in MgI, when this compound is treated with methyl iodide, CH3I, we are getting this product. This compound is produced from the previous step. We can write this was the previous step. This is react with CH3 MgI, and this produces this product plus methane. And this product, when treated with methyl iodide, we are getting this compound LH, this CH3, and when it is treated with CH3COCl, acetyl chloride, CH3COCl, then we are getting this product. This COCH3. So these are the products we found when this detergent is treated with. That is the magnesium product, an organometallic product which is formed during the reaction with Grignard reagent. When treated with methyl iodide, we are getting this 2-methyl pyrrole, and it is 2-acetyl pyrrole. That's all about the reactions of pyrrole. Next we will come to pyridine.